So far, we have just looked at positive series, but in this video, we're going to take a look at series that have both positive and negative terms. There's a couple types of convergence, absolute and conditional, that'll help us with this. So let's start with absolute convergence. So if we start with a series, a sub n, that we're adding up, it will converge absolutely under the condition that the absolute value of each of those terms converges. So for example, does n equals 1 to infinity of negative 1 n minus 1 over n squared converge absolutely? Well, we could start with that, and we could even look at what these terms are. So when you put 1 in, you get 1 over 1 squared. When you put 2 in, you get negative 1 over 2 squared. And this pattern continues with alternating terms. Well, absolute convergence takes a look at what happens if we take the absolute value as n equals 1 to infinity of this same sequence and see if it converges. So each of these terms now just gets added, and that series continues. And you should recognize this is a p-series, and it has a p-value that's 2, which is bigger than 1, therefore it converges. And since it converges, we can then say that the function, or sorry, the series also converges. Absolutely. So in this example, does S, which is the sum as n goes from 1 to infinity of negative 1 n minus 1, the alternating series with root n on the bottom, that's 1 over root 1 minus 1 over root 2 plus 1 over root 3 minus 1 over root 4. Well, if I change this and absolute value this to look for conditional, these turn to positive values. And we will notice that this is a p-series, and this p-series has a p-value that's 1/2 because of the square root, but 1/2 is less than 1, therefore this conditional one diverges, and therefore S does not converge absolutely. However, it's important to note that we don't actually know if this converges. So a series can actually converge without it converging absolutely, in which we say that the series is conditionally convergent. And a conditionally convergent infinite series, so if we have a sub n which is conditionally convergent, will be conditionally convergent if the series is convergent, but not, sorry, I guess more specifically, but the absolute diverges. So we can't use the integral test or the comparison tests because on an alternating series because of every term needing to be positive. What I mean by that is that if we have n equals 1 to infinity of, you've seen this term that it switches the positive to negative, which is an alternating series. If we have some sort of alternating series, so get a positive term, take away a negative term, plus a positive term, take away a negative term, something like this. This will converge still. It will converge still if the limit as n goes to infinity of any of the individual terms approaches 0. And this is known as the Leibniz test for alternating series. And upon closer inspection, this Leibniz test for alternating series makes quite a bit of sense, because if you're adding values that are getting smaller and smaller and smaller, they're decreasing, then it will converge to 0. Let me formalize this. So as I just mentioned, the Leibniz test for alternating series will assume that you have a sub n, which is a positive series that's decreasing, converging to 0. So each previous term is a little bit smaller and eventually going to become 0, which is the limit as a sub n, as n goes to infinity of a sub n is 0. Then when we add up this alternating series, well, the total amount that you have for s will have to be bigger than 0, but less than a sub 1. And as you continue this, it will get converging to 0, which means that it will converge. And we can use this to show some series converge. So let's take a look at one. So we'll go back to this series that did not absolutely converge, but we'll see if it actually does converge, and we'll even see if we can find that the sum, the infinite sum, is between 0 and 1 as well. So the actual terms of a sub n, which is 1 over the square root of n, these are all positive and decreasing. And they have a limit as n gets closer and closer to infinity of 0. So by the Leibniz test for alternating series, S converges. And since a sub 1 is equal to 1, part of the Leibniz test is that the s value will always be between 0 and that first term. So we also will show that it converges to a value, s converges to a value between 0 and 1. And as we saw before, this is actually a p-series. But the p-value, so this is a p-series, but that p-value is a half, which is less than 1. So it converges conditionally, but it does not absolutely converge. So again, it's important to know the difference between conditional convergence, absolute convergence, actual convergence. And we'll explore that in the rest of this unit, and also in the assignments that we'll have associated to this.